Hardware error recovery, containment, and reporting are key features required for achieving mission-critical objectives on modern servers. Today, we have the pleasure to demonstrate their implementation in the I/O subsystem with PCIe Live Error Recovery on an HP Integrity SuperdomeX server running the Linux operating system. Most of the computers today use the PCI Express standard for connecting extension cards. It's based on a serial bus architecture, and errors happening in this subsystem can potentially propagate to other components, resulting in a crash of the entire server. The list of possible PCIe errors is important, and the risk that a fatal error occurs increases with the number of PCIe slots in the server. To minimize this risk in HP's high-end servers, HP implemented specific firmware features leveraging Intel's Live Error Recovery mechanism. When a PCIe error occurs, Intel's Live Error Recovery is able to contain the error, avoiding a crash of the machine. In parallel of this error containment, HP's firmware is informed and stops I/O transfers to avoid corrupted data on disk. It notifies as well upper-layer device drivers and the operating system. HP's contribution to the enhancement of the advanced error reporting PCIe implementation allows Linux to better report the details of such errors in the Linux syslog files. In addition to this vertical reporting path, the SuperdomeX embeds an error analysis engine that records the error details and proposes solutions to field technicians for all possible types of hardware errors. In the first part of the demo, we corrupt a network adapter register of a mid-range server not featuring Intel's Live Error Recovery and running a standard Red Hat 6.4 operating system. In the second part, the same error will be injected in a SuperdomeX running a more recent version of the operating system. The server will survive, and the network traffic will resume after a reset of the impacted drivers. In the last part of the demo, we'll review the log messages of the error analysis engine stored in the onboard administrator of the server's enclosure. From the console of this mid-range server, we verify that it runs a regular Red Hat Enterprise Linux 6.4 kernel. We need now to retrieve the IP address and the PCIe bus location of the Flex Fabric adapter used for the demo. From a remote system, we generate some network traffic toward the adapter. We're now ready to modify a register of the network adapter. The first visible effect is the interruption of the network traffic. Shortly after, the system reboots abruptly. During the restart of the server, a message recommends to check the integrated management log for details of this unexpected reboot. The IML mentions an uncorrectable machine check exception and provides the exact location of the corrupted register. Let's reproduce this error injection in a SuperdomeX with an appropriate firmware and running a newer version of the Linux kernel than the one used in the first part of the demo. This server is composed of two blades, each of them part of a different hardware partition. We'll use partition number 5 for our experiments. In this part of the demo, we'll corrupt a register of Ethernet card ETH4, part of partition 5. To do so, we need to retrieve the location of this card on the PCIe bus. Its IP address is required as well to create some network traffic from a remote node. When we recorded this demonstration, Red Hat Enterprise Linux 6.5 was still in development mode. This is why the kernel version number returned by the uname command contains the combined suffix. The date command issued before the set PCI directive will display a timestamp used to identify the test in the different log files. Immediately after the error injection, we can see numerous hardware error messages in the console window, and the network traffic is interrupted. After a while, the network traffic resumes, and a device recovery successful message appears on the console without any machine check exception encountered. On this development platform, it took several minutes to recover. Today, on production systems, this time has been reduced. In addition to the kernel ring buffer error messages displayed on the console, the syslog daemon has been notified and reports some details in the messages log file. The Onboard Administrator module of SuperdomeX servers embeds a unique error analysis engine monitoring constantly the different hardware components of the platform. Hardware errors are analyzed by the engine, which can take automatically concrete actions and notify higher-level management tools, local or remote. In our case, we triggered a PCIe error that must be present in the Error Analysis Engine's database at the time we injected the error. Given the ID of the error, the EAE displays a complete description, possible causes, and recommended actions to be taken on identified faulty components. With features like advanced error containment, SuperdomeX enables you to maximize the uptime of your critical Linux applications. Delivering proven availability, breakthrough scalability, and groundbreaking performance on x86 efficiencies, SuperdomeX can help you transform your mission-critical environment in ways that have not been possible before. For more information, visit us at the link shown here. Thank you for watching.